Welcome to the Indian Academy of Sciences Jubilee Chair lecture. Today this lecture will be presented by Professor T. Venkatesan, Tirumalai Venkatesan, who is the Indian Academy of Sciences Jubilee Chair Professor. He is visiting many institutes in India, and IASc is one of them. Perhaps the first institute is starting at IASc. So I'll very briefly introduce Professor Venkatesan to you. He is currently with the Center for Quantum Research and Technology. He is a professor of physics and ECE at the University of Oklahoma and scientific affiliate at NIST Gaithersburg. He is a senior advisor to the Office of Vice President for Research. As the inventor of the pulse laser deposition (PLD) process, he has over 800 papers and 34 patents and has a phenomenal citation index with 58,000 citation and H index of 121 as per Google Scholar. He's been recognized by many institutes across the world. He's fellow of the Royal Society, National Academy of Inventors, foreign member of the Indian National Academy of Science, Singapore National Academy of Science, Asia Pacific Artificial Intelligence Academy, World Innovation Foundation, APS, that's American Physical Society, Material Research Society, MRS, Academician of the Asia Pacific Academy of Materials, winner of the Belcourt Award of Excellence, Georgie Peck Prize Award by APS, Distinguished Lectureship on the Applications of Physics Award, APS, President's Gold Medal of the Institute of Physics, Singapore, guest professor at Tsinghua University in China, and he was also the past member of Physics Policy Committee, the Board of Visitors at UMD, and the Chairman Forum of Industry and Applications of Physics at APS. He was awarded the Outstanding Alumnus Award from two IITs, that is IIT Kanpur and IIT Kharagpur. He has founded 6 high technology startups and is the president of Neosera and CEO of Neosera Magma, companies manufacturing equipment for specialty coatings, and also semiconductor fault location. And he is very well accomplished. Without much ado, over to you, Professor Venki.
I want to thank Professor Navkant Bhatt for hosting me here at the Institute of Science, and I've already had a wonderful day here, meeting with so many people, and meeting my other colleagues and former graduate students and so on, which has really been exciting. Yeah. I look back at 1977. One of my first lectures that I gave after my PhD was here in the physics department at the Indian Institute of Science, actually. So that was like, what, 50 some odd years ago, almost. So, I mean, I've had a pretty long journey. My career started at Bell Labs, and then went to Belcourt, and then to University of Maryland, the National University of Singapore, and now I'm at Oklahoma. It's been sort of almost went around the world once, like Magellan, basically. Yeah, and I mean, the interesting thing is that I mean, you start as a physicist, but you end up as a problem solver. I mean, that's the story of my life, basically. So I don't have any specific tags anymore. I try to solve problems depending on whatever field it is in. So the thing is that there used to be a time when I used to say, oh, I'm doing fundamental research, it's of no value to society. You kind of hang it like a badge of honor, basically. But now I realize that you can actually work on solving world's problem and at the same time do really fundamental stuff. So it doesn't have to be at the expense of one or the other, basically, right? So I'll give some examples of the various kind of work we are doing here, So I picked a number of topics, and but they're all interconnected, So I'm going to talk about, extreme weather, which is really one of the major global challenges that we're facing today, And I mean, literally no week goes by without reading about some disaster in some part of the world, Last week it was Spain. I think this week it's somewhere else. I mean, I'm sure in Bangalore you guys experienced 4 weeks ago some major, downpour, etc. Right? So I mean, our only defense against today is essentially better weather modeling and prediction. That's our only escape from extreme weather. No way are we going to turn back the clock on this one, basically, right? I mean, then that raises the next question. The energy, our fossil fuel has been partly responsible for where we are today in terms of the extreme weather conditions. And so therefore clean energy, and I want to talk to you about fusion, which is there's been a tremendous amount of excitement lately about nuclear fusion as an energy source, and where are the opportunity for us to contribute to that. Okay, so I'm going to talk about that. Then, because of the extreme weather, rises in temperature globally, right? You have now new pathogens that are emerging, basically, you know. And for example, recently we went through, just barely a few years ago, I mean, COVID-19 was a major one that really affected us in a big way. But that's not the end of it, right? In the near future, there are going to be more variants of bugs that are going to come along. I mean, Germany, for example, right now, they have incidences of malaria coming back, you know, which is completely unheard of, basically. And so disease is going to be a big deal, and early detection of disease is going to be very important. Okay. Then the other area which is of interest to me is semiconductor advances. I mean, and again, this is energy related in a way, because what you're trying to do is you're trying to put more functionality in small volume with lower energy consumption. And I want to talk about something called heterointegration, and an area that, you know, my own work relates to that. Okay. And of course, what is connecting all of these stuff? Okay, so if you really look at it, essentially, the reduced energy consumption is a very important parameter that connects all of them. Another one is improvements in material technology can actually be also things that could affect many of these, but enhanced use of AI/ML is another thing that's becoming very common to all of them. And I'll show the, you know, correlation between how AI/ML gets used up in all of this, right? And when we talk about AI/ML, improved electronics for AI/ML and memristors is another area which I'll touch upon. And last but not least, quantum computing, developing, which is really alternate, you know, ideas, you know, in quantum computing. So I'm covering a lot of ground here, but they're not like completely disconnected ideas, but they're all connected in some way. Okay. So let me start with weather. Okay, and so extreme weather. What is the need and what's the significance? And so this was actually in 2022. Roughly about 2.5 million people were displaced because of bad weather, okay? But I'm pretty sure in 2024, just in Florida alone, this number is probably reaching pretty close to a pretty large number right there. You know, the recent two hurricanes, basically Helen followed by Milton, completely upset one complete state in the United States, right? And for example, the World Economic Forum put out this graph which shows what is the likelihood of something happening and then the impact of a risk. Okay, so this is basically various kinds of risks. For example, weapons of mass destruction is up here. It is probably will have a major impact to humanity, but the probability of happening is very low. So the likelihood is very low here. You can sort of see here. On the other hand, you look at climate-related extreme weather, climate-related failures, all of these are up here. They're very high impact and very high probability, you see. So this is really if I call it a global challenge, it's not an understatement, right? It's truly a very important issue to be contended with, okay. So what I did was like, well, what is the need and significance? And sitting in Oklahoma, which is kind of the epicenter for weather modeling, climate, and weather prediction, right? So what I felt was one thing we could do, can we propel India to the forefront of monitoring and forecasting climate and weather and the water phenomena, okay? So essentially, co-create better decision-making processes for climate reliance and adaptation, resilience and adaptation, and eventually forge global collaborations to tackle complex challenges, okay? So what we wanted to do was, I wanted to create a an ecosystem of academics and operational agencies in India, the US and abroad, to forge a global collaboration to tackle this challenge, basically. So that was the idea. Then the question is, why OU? It turns out in the United States, the weather pattern is determined by cold front coming from the north and warm front coming from the Gulf, and they clash. When they clash, they create extremely extreme wild weather effects. And Oklahoma is right at that boundary, basically. So in Oklahoma, you have some of the most extreme weather patterns. Just day before yesterday and yesterday, there were, essentially tornadoes. Series of tornadoes just struck the state, basically. And all my friends, I got like 20, messages on my cell phone. Are you okay? Are you okay? Everybody writing to me. I'm sitting happily in Bangalore. But all my friends are crouched in the bathrooms and hiding in various places. That's how severe weather can get, right? Now the interesting part is the weather pattern is completely shifting in the United States. Right now, that entire tornado alley is shifting to Georgia and towards Florida now. It's slowly moving eastwards, right? Because of this weather changes in the world. And it won't be surprising if India will also start experiencing more and more of these phenomena, basically, right? So Oklahoma is basically, because of its severe weather, has learned to manage weather and has become the epicenter for weather and climate. The cutting-edge weather modeling and prediction works, including AI/ML, is going on there. Advanced Radar Research Center, this produces some of the most advanced work in radar for weather prediction, and there's a rad, unique combination of private industry, academia, and federal and state organization all working together at the National Weather Center. Okay, so they all crowd around this building here, and essentially you find graduate students, you find industrialists. It's a very interesting melting pot, right there. The multi-radar, multi-sensor group. Like if you go to any American weather TV channel and you open it, you see these radar patterns and all this stuff. All the technology is made by this group, multi-radar, multi-sensor group, and they have the National Severe Storms Laboratory, which really develops the state-of-the-art for tracking, hurricanes and storms and other stuff. And there's also an Institute for Public Policy Research and Analysis. We all work on, policy challenges associated with extreme weather. So these are all, we want to bring all of this to India to create an ecosystem in India which is similar to the US. So that was the idea that I came in with, right? So about a year ago, I came to India, met with the Indian Meteorology Department, and also with Ajay Sood, our science advisor, and he basically introduced me to the Ministry of Earth Sciences, Dr. Ravi Chandran, the secretary, and so they put together a plan now, and we now have a collaboration established between Indian Institute of Tropical Meteorology and University of Oklahoma, and in 19th of this month, we're going to be signing an MOU in New Delhi at the ministry, basically. So this is really what is going on. So I mean, some of the really exciting next frontier is going to be this, basically. Conventional radar antennas are generally very large dishes, which are kind of like mechanically moved, and it takes a long time for them to scan the whole entire horizon. Okay, so today the fastest at which weather gets updated is roughly about 2 minutes, basically. But now this is what is called a Horus, which is the next generation radio antenna. This is basically it's a phased array antenna, and essentially has no moving parts, electronically tuned. Okay, so this would basically reduce the time from 2 minutes to a few seconds, basically. So this is the next generation radar technology that's coming up. So what we're going to do is, with Indian Institute of Tropical Meteorology in Pune, what we're going to do is, under the IITM, there are radar locations in the Western Ghats, Mumbai, Bhopal, Sholapur, and Delhi. So it's a small micro world of India where we want to build essentially a network along with the mesonet. Mesonet is essentially local weather stations. So every region will have like 30, 40 weather stations, and they all produce, data like temperature, humidity, and all the stuff, right? So you got to integrate these data with the radar data, with the satellite data, and integrate them all and feed it to a centralized facility, right? So this is actually a very significant data management problem with, communications involved, okay? Because very large amount of data, so you have to learn to process them and get them all in time very quickly, right? So this is what we hope to do, demonstrate that in this, under IITM basically. And if this entire thing will have the same algorithm that we used in the United States. So once this is improved, then we'll probably adapt it to the rest of India basically. That's a hope right now. And along the process, what we really want to do is, so this MOE kind of covers all of this stuff. The initial work will focus on this, just what I described right now, and essentially transfer and then eventually we transfer all this knowledge to IMD. And we are right now working on a possible joint workshop at the Royal Society. And then the long-term strategy, we want to elevate this collaboration to a higher visibility level in the Indian government and bring the Indian academic weather community into this collaboration in a bigger way, and sort of try to create effectively the same infrastructure like in the United States. That's kind of the hope. Okay, so let me go on to the next topic, which is essentially clean energy, right? So in clean energy, what is the next exciting frontier, and which is nuclear fusion. And I'm primarily going to talk about, there are two types of nuclear fusion. One involves what's called a tokamak approach, where we use very large magnetic fields and a plasma, and confine a plasma and try to, essentially inject as much energy into a plasma as possible so that temperatures will be there like that in the sun, and you will have nuclear fusion basically. So that's what's called the tokamak approach. The second approach is inertial confinement. In inertial confinement, you take a target, which is, I'm going to describe that in a minute. You take a target which is about the size of a peppercorn, and then you bring in a number of laser beams. In this particular case, in Lawrence Livermore National Lab, 128 high-power lasers, roughly, essentially 64 from the top, 64 from the bottom, and they all simultaneously blast this little, poor little, peppercorn. And the target looks like this. The fusion target essentially is a 20 micron thick diamond shell sphere, basically. Okay, how do you produce this? You take a silicon sphere, perfect silicon sphere, about 1 millimeter in diameter, and then use a CVD process, and we grow the diamond on top of it. So the diamond is grown on. Then what you do is you drill a hole in the top, and then you put in some kind of a solvent which dissolves the silicon away. So the silicon completely goes away. You get just the diamond shell. Then through the same hole, you inject deuterium and tritium, and this is done in a very low temperature. So the deuterium and tritium goes in and forms a liquid layer on the surface of the stuff. So that is your fusion fuel, basically. That's a fuel. Then what you do is you essentially inject this ball into a gold cylinder. This is a cylinder of gold. It's about 3.3 millimeters in diameter, and you drop this inside, and then roughly as soon as it comes here, about 64 laser beams come and hit the metals from the top and from the side, from the bottom, and these laser beams end up generating a huge amount of X-rays, and these X-rays then compress this little target basically, and the target gets compressed to extraordinarily high temperatures at which fusion occurs, nuclear fusion occurs. Okay, so this is how this entire thing works. So you can see this is a historical evolution of how this process of work. These are all essentially what called the pressure time product here. Here, essentially, these are fusion events that have been successful, and this started happening only just a couple of years ago. About 2-3 years ago, essentially, this is what we saw. Essentially, 2 megajoule of laser pulse was delivered, and then the energy produced was about 3.15 megajoule. This is the first time this happened, and which means that you have more energy coming out of the target than what was put inside, right? So this led to, amazing excitement in the United States and all over the world. And in the last 3 years, there's been an amazing number of fusion companies formed. There are 45 nuclear fusion companies around the world today. You wouldn't believe it. It's like 45 companies have been formed all across the world, which is really one of the fastest growing industry right now. And so you can see the second ignition, third ignition, fourth ignition. Why does it take so long? It takes like months before each ignition. It is because this target has got to be perfect. If the target has got even small imperfection, it doesn't work, basically. So it takes them a long time to get a right target made. It's material science. How do you make such a target, right? So this is where we can contribute, basically. How can we make a target better and so on. So right now you can see the gain has become significantly large. Ultimately, in a nuclear, this power plant, a fusion power plant, the lasers will be firing at 10 hertz, basically 10 shots per second, and power will be generated. It will be essentially a 100 megawatt plant, basically, 100 gigawatt plant, sorry. So there are right now Lawrence Livermore is collaborating with a lot of institutions, and you can see University of Oklahoma is one of the many working with them. And what do we want to do? Okay, so essentially what the Lawrence Livermore folks want are accurate neutron flux measurement, gamma ray measurement, etc. All of these different things. And so among the many problems that we can contribute to, my laboratory could contribute to, for example, detectors. So what are the nuclear pathways that are there? So I just want to ignore all of this stuff, but just focus on just this top part. Deuterium plus tritium gives you, there are two pathways here. One is the nucleon branch and this is a gamma ray branch. In the nucleon branch, you essentially produce an alpha particle and a neutron. In the gamma ray branch, you will actually produce, essentially another charged alpha particle plus now you'll produce a gamma ray here. So both of these are indicators of the quality of your fusion, and people try to measure these things. Okay, so these are the detectors that are needed for. For example, these are gamma rays produced, spectrum of gamma rays produced in a nuclear fusion. These blue things actually come from the gold cylinder, so this is really of not much value. But this line which is here, this gamma ray comes from the implosion of the diamond shell, and then this gamma ray here, which is roughly around 16.7 MeV, this really comes from the actual nuclear fusion. So if you can measure these gamma rays very accurately, you can actually predict how good your fusion is taking place. So how are gamma rays measured? So they use something called the Cherenkov neutron detectors, and what happens here is you take a quartz rod, and this quartz rod can be about a centimeter in diameter. When a gamma ray comes and hits this quartz rod, the gamma ray pushes an electron out from the atom by what's called Compton scattering, and this electron then has a lot of energy, and if the electron energy velocity exceeds the phase velocity of light, it starts producing light, and that light is called Cherenkov radiation. And the Cherenkov radiation then gets guided by this glass tube. It's like a fiber, and then it gets collected by the detector. Okay, so this is how you can measure this as Cherenkov radiation radiation. Now the way you measure the neutron is the same detector can also measure the 14 MeV neutron, and the neutron hits this, it generates a gamma ray by another scattering process, and this gamma ray then again converts to Compton electron, and then the Cherenkov radiations. So it's very interesting. This whole detector is a very interesting process. Okay, so the Cherenkov radiation produced per unit length is given by this equation, where basically you can see this denominator it's got to be essentially greater than 1 for it to work, and that condition is exactly saying that the electron velocity has got to be greater than the phase velocity of light in the material. Okay, so that the phase velocity of light in the material depends on the refractive index of the material, right? So if I want to measure lower and lower energy electrons, I can reduce the essentially refractive index, and I can go to higher and higher gamma energy basically by reducing the refractive index. So this is a very interesting thing, and so in the same detector, I can detect both the gamma and the neutron essentially in time space. So this is like a time dependent measurement. The gamma is traveling at the velocity of light, so it arrives first. So this is the gamma signal. The neutron sort of comes hobbling along, and you measure it later, and this is almost a 450 nanosecond time difference, right? So you can do time resolved measurement of this stuff. So this is the kind of stuff that we can do. So what we're doing is I'm taking that idea, this little more idea of a Cherenkov detector, completely converting that into a different geometry where the neutron and the gamma beam comes straight into the detector. So we can now create a two-dimensional image of the detector through and detect with a camera. So that's what I'm working on basically. So I'll give you some example of what it would really look like. So this would be what would be a pinhole camera image of the nuclear fusion site. So this is how the neutron distribution is coming out from the site, and how close to this is like a circle, perfect symmetrical circle, tells you how good your fusion reaction is, right? So this is what you're trying to image basically, this neutron that you're trying to image, create a detector imaging. So that's what we're working on. And one of the interesting things there is, if the gamma ray, the minimum energy gamma ray that I can measure depends upon the refractive index of the material. And you can sort of see, if I want to measure the 16 MeV gamma, for example, up here, the refractive index of the material has got to be just barely above 1 basically, right? And so the way they make this is they use what's called a gas-based Cherenkov detectors, and this is like a huge cylinder. It's like a gas cylinder, and they fill it with carbon dioxide. They put a beryllium at the front end, and you know essentially the gammas that come in here then will create Cherenkov radiation through the electrons that are generated in the beryllium, and they will create Cherenkov radiation, which then detected by the detector here eventually. But you see, this entire thing is huge, it's about this big, you know. So one of the ideas that I'm proposing is that, listen, we can use essentially what are called near zero epsilon materials, right? Near zero epsilon materials, so we can contract the size of the entire thing and make it into a much smaller form factor. So that's one of the things that I'm working on. Okay, so there's another idea that we're working on, and that is, in the fusion reactor, they need to measure the beam profile of the lasers, and they want infrared up converters. These lasers are all at infrared, and they want them to convert them to visible. And the way you do that is, if you take a nanoparticle, and these nanoparticles are doped with rare earth element like thulium, for example, then this core shell nanoparticle does an amazing job of converting infrared intensity into visible light, basically. And so this light, which is around like anywhere between 1 to 1.5 microns, gets converted into 800 nanometer basically here. So this is basically, there's a power law here, which is like 15th power law, and this is some kind of an avalanche effect where every thulium atom excites the next thulium atom in the next sphere, etc. So how do you produce these nanoparticles, right? And so this is where I've come up with a very cool idea, and the idea is like this. We take nanopillars of silicon, right? These are silicon nanopillars, and then on top of these nanopillars, we deposit our layers using pulse laser deposition. And in PLD process, what happens is, it's a forward directed process. There's no sidewall coating. So the coating, all the coated layers sits right on top of the pillars. You can sort of see like here. Other stuff goes in the middle, right? So here, for example, is a sort of a beautiful nanostructure created, and this could basically have multi-layer structures in it, and you can produce. This to me is the modern way we're going to produce nanoparticles in the future, basically, right? This is it. You can now produce identical nanoparticles, identical sizes, and these particles, I can produce them in billions, basically, right? So this could be a very, very exciting technology. So let me not spend too much time on this. So now I want to pass on to the next topic, which is health-related thing. How are we going to, take care of, emergent diseases and with rapid screening technologies to protect ourselves, okay? And in the United States now, what is happening is a new phenomenon is occurring, and that is young people are getting cancers, okay? People at the age of 20, 25 are getting diagnosed with cancers, okay? So it may be because of emergence of new materials in our environment, we introduce all kinds of new technology and stuff in the thing, and they may have a carcinogenic effect on us, right? We don't know. But the survival rate in most cancers is, if you catch them in stage 1, you have an 85% chance for survival. If you catch them in stage 4, it's 5%. You're pretty much terminal, basically, at catching in stage 4. Most cancers are caught in stage 4, unfortunately. That's a problem, and that's why cancer is a disease which is so deadly, But if you can diagnose ways to measure cancer early, then we can truly protect ourselves. So one other technology we're working on is called BrainIt. We call it BrainIt. It's breath analysis using AI integrated, invasive technology. Okay, I was told that there is some IT company who's got the same name, so I'm a little worried about the copyright violation right now. But anyhow, that aside, we'll address that later. What's the idea here? So in our body, in our breath, we produce what are called volatile organic compounds. Okay, I mean normally in your breath you have carbon dioxide, nitrogen, oxygen, all of the standard stuff. Those are all like 10%, 15%, that level, right? But at parts per billion level, right, we are like a molecular factory. We produce 3,000 organic molecules our body produces. And what are these organic molecules? They come from the cellular processes. If you think of a cell as a small motor car, it's the exhaust of the motor car. all these organics are your cellular exhaust. And what do? They get excreted from the body in multiple ways, but many of them dissolve in the bloodstream, and they come to the lung, and they come to the alveoli in the lung, and the alveoli cleans up the blood and puts all these gases into the breath, basically, right? So if a cell gets diseased, what happens? The molecular pattern changes. So by looking at this pattern of these molecules, you can actually predict. So this is a crazy idea I had like 10 years ago, and what happened at the same time was there was a new mass spectrometer that was introduced in the market called proton transfer reaction mass spectrometer. What is amazing about this mass spectrometer is, in a conventional mass spectrometer, the molecule that you put in to analyze has to be first ionized. And the way they ionize the molecule is using electron beams. So ionizing a molecule with electron beam is like trying to crack a peanut with a sledgehammer, Yeah, you will crack it, but you also crush it, basically. So these molecules get crushed, they get into many, many pieces. So you get like a fragmentation pattern, and they've developed algorithms, like Thermo Fisher has fancy algorithms to, essentially get from the pattern what the molecule is, but you lose a lot of sensitivity. You lose orders of magnitude sensitivity. But in this spectrometer, the way they ionize it, they bring in a free radical, attach it to the molecule, and create an ion out of it. And so this doesn't break the molecule. It doesn't fragment. So this spectrometer has got a sensitivity which is part per trillion. So it can measure 1 part per trillion a molecule. You sit in that part of the room and you open a glass of wine, it'll measure. Oh, the alcohol will go crazy here. It can measure that molecule. That's sensitive. So this is the basically the proton transfer reaction mass spectrometer. It's on wheels, so you can roll it, put it in a van, you can take it somewhere. So it's reasonably mobile. Okay, and this is essentially a hose, and this is the mouthpiece, and you can see a person breathing into the into the machine here. Okay, so this entire process is a very, very fast process, and what we do is here's the number of patients that we studied, and so here's the name. These are the different patients, and we put down the age, the gender, all the different information, and these are the different molecules. And I'm just showing only a small number of them here, but we collect data from something like hundreds of molecules. Okay, and then what we do is we do a pattern recognition algorithm, and then from that we can predict whether you have a particular disease or not. Okay, so I'm going to show you some actual data. This is a study we did in Dubai. We spun off a company called Breathonics. This is the first spin-off company that made a ton of money because we spun it off right during the pandemic. So after we spun off the company, 7 months later the pandemic struck. So we quickly developed a Breathonics thing for COVID. So this machine would essentially detect in a person 60 seconds COVID test, basically. You breathe into the machine, it tells you in 60 seconds whether you have COVID or not. So we rapidly started selling this machine to Vietnam, Thailand, Singapore, Dubai, all these places, all of these places. And they started putting them in the airport entry places and all this stuff. Right? So we started taking this and saying, okay, forget about COVID, let's look at other diseases. Can we look at them? So we're looking at, for example, human rhinovirus, human coronavirus, this is the, this thing, streptococcus, pneumonia, and the influenza. So there are 4 different diseases. And you can see 4 different colors here. And this is essentially, this is a multivariate analysis, and where we actually essentially plot what are called principal coefficients on the x and the y axis, and it enables us to take the data, which is a it's a multi-molecular data and multi-people data, but convert that into like a 2-dimensional plot like this, right? So if you look at this plot, you can see, can you separate them out? You can sort of see this is the pneumonia patients. These are all basically the coronavirus patients, and then you have these red one, which is basically the rhinovirus. So you can see these are actually separating out. You can see, and you can statistically come up with the formalism to separate out, whether one disease is, a person has one disease or the other. Okay, so I'm going to show you a little bit more detailed study of, for example, how we look at lung cancer, for example, and this is where we did an extensive study on lung cancer and even published on it. So the different molecules in the breath, okay, and you can sort of see the green belongs to the healthy person, red is the lung cancer patient. So this is the data acquired from a large number of patients. In this particular case, I'm comparing 50 healthy people with 50 cancer patients. You can see this molecule, this particular molecule, the red and the green are well separated. See, similarly here is separated. The one that I just kind of marked out in this dotted line, there you can see a separation between them. But the others, you don't see much separation, right? So let me show it in a different form. I plot these things in a, like this. So these are different molecules now. I'm just giving you the number of the molecule, the effective weight, molecular weight. So you can see this is the normal people. This is the concentration. This is people with cancer. This is increasing concentration. So in the cancer patient, this molecule is excess. Similarly, in this molecule, it's in excess. So you can see these are a select number of molecules I pulled out of that list, where you can see that the lung cancer patient definitely have a difference between a lung cancer patient and a normal patient, right? So we can use this now, and you can look at, for example, the principal coefficient analysis, and you do that, you see these are all the lung cancer, these are the lung cancer patients, and these are the healthy patients. So if I get your breath data, and your data point comes here, somewhere in this range, you're normal, you're okay, you don't have to worry. But if a data point comes like you're out here somewhere, then you better go for a checkup. Really, you could potentially be a lung cancer, patient, basically, right? But this test takes 60 seconds, right? There's no biopsy needed. The problem with lung cancer is, when they detect lung cancer, they do it with a CAT scan. So you sit on a CAT scan machine, it takes, 45 minutes, an hour to get it. It's very uncomfortable. You're sitting there and you're getting exposed to X-rays all the time, right? And then you get a data, and then they look at your lung and say, oh, there's a nodule there, right? Then you're in a quandary. Then the doctor will say, you have a nodule in your lung, you could potentially have lung cancer. But then the question is, what do you do next, right? So to do a biopsy, you have to take a piece of the nodule to see is it cancerous or not. But inside a lung, taking something out from inside your lung, your lung is like a balloon, right? So you're going to pierce, you're going to put a fine needle through your lung to pick out the biopsy. That itself is a very risky process. There are very few people who know how to do it right, and it's a very dangerous process. And so most doctors say, let's wait and see what happens. Come back in 6 months, we'll take another CAT scan, right? And so all these cancer hospitals have a lung cancer library. So the library is basically a nodule library of all the people with stage 1 lung cancer, waiting to know whether it's growing or it's not growing with time. So it's completely this thing. If you had a test like this, if you could in stage 1, you could detect it, then they can make a more informed decision as to whether they want to go for this thing or not, right? So that's why this is a very important thing. So what I did is, in the University of Oklahoma, another big deal is the university itself is split into two. One is the Oklahoma Health Sciences Center and the University of Oklahoma. So it's a $2.5 billion enterprise. About $1.1 billion is the University Health Sciences Center, and the $1.4 billion the University of Oklahoma. And we are separated by 20 kilometers, basically 30-minute driving distance, And our cancer center there in the Health Sciences Center has got a number of clinicians who want to do research, right? So I went to them and I said, look, let's go for a MacArthur Award, this thing, and we're going to look at 15 different cancers with one breath. Okay, diagnosing 15 cancers with one breath. We're going to do that, right? So this is the presentation that we made for that, basically.
With early detection, lives can be saved, but current diagnostic methods are often invasive, costly, and inaccessible, especially in underserved communities. In many parts of the world, people lack access to early diagnostics, leading to late-stage cancer diagnoses and higher mortality rates. The need for an affordable, non-invasive, and accessible solution has never been more urgent. Breathomics is that solution. By analyzing volatile organic compounds in exhaled breath, our groundbreaking technology detects early-stage cancers in under a minute. This non-invasive, painless test is not only quick but also affordable, making it accessible to communities around the globe. What sets Breathomics apart is its ability to reach underserved populations. Our portable screening units bring this life-saving technology directly to those who need it most, breaking down barriers of cost and accessibility. With the support of the MacArthur 100 and Change grant, Breathomics will be integrated into healthcare systems across the US, Singapore, and India. Our goal, to reduce cancer mortality and improve outcomes for millions, particularly in underserved communities. Together, we can revolutionize early cancer detection and make a lasting impact on global health. Thank you for your support.
So, I want to show, for example, when you get a data like that, then you have to use neural networks to do prediction. And I'm showing here 4 different, in this very small population set that I had of 50-50, right? There are 4 different network models that you can use, and they all have different, accuracies. You can see here, for example, this one has essentially something like 98% accuracy in predicting cancer, 88% for COVID, right? Whereas here, and just predicting whether you're normal, this is like 100%. Whereas in this case, it's like 98%. So this variation, the same, for example, this predicts cancer with 98% accuracy. One COVID with 88%, this guy does 90%, 82%, whereas this one does COVID with 98%, but cancer with 86%. So there's some variability in the same different networks that we're using among different diseases, right? So I don't know whether it's because of the small set we are using, which I think is probably one of the reasons. But our goal is to get larger sets. I'm talking about like 1,000 patients, 2,000 patients, right? And that's the reason why we're trying to form this collaboration, Site Care, in Bangalore. And my hope is we have a meeting set up with them to try to see how we can expand this to a very larger base and rapid acquisition. So anyway, now I come to my next topic, which is semiconductor technology, and and what are some of the pressing problems in semiconductor today? So there are basically, the semiconductor industry is trying to do two very important things. One is staying on the Moore's law curve, that which means trying to make the transistor smaller and smaller, right? And essentially, that the number of people doing that has dropped from like 12 or 15 in one day. Now this is basically Samsung, TSMC, okay, pretty much it, okay. Intel pretends to be there now, but Intel just got knocked out of the NASDAQ. They're no longer even in the stock market. They were pushed out of the NASDAQ. I mean, really, they're going through a pretty inglorious time right now, And the other approach is what's called hetero-integration, okay. Here, what we're trying to do is, how do I take multiple silicon wafers and combine them with a lower generation technology? I'm talking about like gate lengths of silicon at say 128 or even 90 or even that sort of levels. But I can put many of these chips in a small and create a small volume, but the functionality is now multiplied significantly, right? And it's called hetero-integration. So how do I increase functionality more and more? So in this process, one of the new development that has occurred is pulse laser deposition, the process that I invented, is now going into a fab now. And so that is a big opportunity for us. Basically, I know within Indian Institute of Science, at least 6 professors use PLD here, So, that means there's a workforce for the future. All the stuff we're developing could be very useful in the semiconductor thing. And also integrating multifunctional materials on silicon now. So on a silicon, integrating optoelectronics, integrating piezoelectric materials, or for MEMS, those kind of stuff, right? That is integrating other functional materials, right? And so I'm going to talk about some of these things, which are very interesting opportunities. So this is Lamps. What they just came out with big news about introducing a pulse laser in the fab. So they're now introducing it in the cluster tools in the fab, and they basically making 15-inch wafers with this stuff. So one idea we are working on is a technology called low-angle X-ray spectroscopy, which will enable us to measure the composition of the film as you're depositing the film, okay? As you're depositing the film, so what happens, the film is being deposited, the laser comes, strikes a target, material goes up, deposits on your substrate, and then there's an electron beam that measures the film that is being deposited on the substrate. We use this electron beam anyway to measure the crystallographic orientation of the film and so on, and also the film thickness. But the electron beam also generates X-rays when it hits a film. So can we use the characteristic X-rays to measure the composition? That's a thing. And this has been a problem that people have been working on it for like 25 years, and people have not been able to solve that problem. So in my company, Neosera, I had a mad Russian who basically was absolute genius. He came up with an algorithm to solve this problem, So let me kind of quickly show you how it does. So this is essentially the X-ray detector here, and this is basically, there's an electron source from the other side. The substrate is somewhere here, and X-rays are generated and measured here, okay? So now, I just want to show you the results. And the way it works is, we measure the X-rays produced as a function of time, and we extrapolate the X-rays produced with a characteristic to 0 thickness, basically. At 0 thickness, essentially, all the problems like self-absorption of the fluorescence, and re-emission from different depth areas, all of these problems which cause confusion go away. So you essentially go to the 0 thickness approximation. So this algorithm, that's what it does. As the film is growing, it constantly extrapolates back to 0 thickness and gives you the composition. So here, for example, is a composition of a complex film here. Lanthanum 0.678, calcium 0.32 Mn. This is the composition measured instantaneously as the film is growing. Okay. Then we take the film, we send it to California to Charles Evans. They do Rutherford backscattering and they measure it. The film comes back to us 3 weeks later, right? And look at the composition of the same film. Okay. Lanthanum 0.67, calcium 0.32 MnO6, right? The difference is we got this number instantaneously as opposed to waiting for 3 weeks, right? So this is going to be extremely important. We can even do this on a combinatorial library of materials. So this is a wafer with different materials, and at each point we can actually measure the composition, very interestingly, So this is something which will be very useful for the semiconductor industry. Another area of great interest is how do you grow crystalline oxides on silicon, epitaxial growth of functional oxides on silicon. And the problem with that process is most silicon wafers always have a native oxide on top of them. Typically, a few tens of nanometers of native oxide on the surface. So, when you grow an oxide, any other oxide, you'll never seize the silicon template. So, how do you make it grow epitaxial? So, what we've done is now we have actually shown that this is a yttrium stabilized zirconia film. So, you can see this is the YSZ film that is grown on the silicon, and it essentially literally a single crystalline film that we're growing right now of this YSZ on silicon. Just starting with the native oxide on silicon, the YSZ has such a strong affinity for oxygen, it just eats up the oxygen and goes to the surface and grows epitaxially. Just an amazing material system. Not only that, we are now growing cerium oxide, cerium oxide, indium tin oxide, magnesium oxide, and tungsten dope indium oxide. We're now growing a whole range of different oxides directly on silicon in a crystalline way. But the one that I'm going to talk about now, which I think is going to be one of my most favorite inventions, this is really exciting. And this has to do with the fact that when we grow these oxides like, optoelectronic material like lithium niobate and, even barium titanate and all these materials, they're very difficult to etch and pattern them, right? The patterning them is a real problem, okay, because they don't etch easily. On the other hand, we can etch silicon beautifully, create lovely pattern on silicon. So what we do is we use the silicon wafer, pattern it the geometry we want, then we use PLD to deposit the oxide. And the PLD is a very forward directed process. It doesn't cause sidewall coating. So that's what happens. So you see, and let me show you. So you see here, this is a silicon pattern to a wall about this tall wall basically, right? And this is an oxide of yttrium stabilized zirconia grown on top of the silicon basically. So similarly, here's a little cap of YSZ on top of this little pillar of silicon, and there's like 200 nanometer pillars, and you can see they're all the top of the thing. You create this little discs of YSZ, and these are single crystal films basically, And so we can do that for the things like cerium oxide. We can do the same thing for cerium oxide, and this is tungsten dope indium oxide. These are conducting oxides, and you can see even like 100 nanometer pillars, and this you can form these beautiful structures on top of these things. Right? Yeah. So I think this is going to for example, we are working on, for example, trying to create a crossbar array and also things like optical resonators and so on. Will be the next stage, So my vision is one day we're going to have an AI/ML program that designs an optical device. You say, I want this device to do such and such a thing, and it'll be designed by AI/ML, and that program will go into a reactive ion etcher. Your silicon will be patterned, goes to the next PLD oxide deposition system, deposits the oxide, and out comes your device. Basically, that's kind of what's going to happen basically in the future. Right? Yeah. So in the advanced packages that I talked about in the semiconductors, there's another big problem, and that problem is today when you take multiple silicon wafers and you make a package out of them, they become very thick. And every time you make a new package, they will always not be perfect. There will always be some problems with the chip, and you have to locate the faults first. Where is the fault? Where is it? And where did it occur? You have to do an analysis, right? And The problem is that all the analysis technique that we have today for looking at chips, they only work up to like a few microns thickness. So when things get to like, 1 millimeter, 2 millimeter, nothing penetrates. Light doesn't penetrate because the ground plane will stop it. Heat will not go that far because the ground plane will diffuse the heat away, right? So the only thing that penetrates it is X-ray and magnetic field, okay? But magnetic field is not sensitive to electrical signal. Magnetic field, the X-rays can only detect, density differences basically. But the magnetic field can look at, shorts, all those sort of stuff. So essentially so this is the technology that we have developed, which is called essentially, we use 2 quantum magnetic sensors, and these magnetic sensors scan over a circuit here at the bottom basically. And then the circuits produce magnetic field which come up from the circuit and is detected by, then you create a 2-dimensional map of the magnetic field, and then you Fourier transform it, and then you get all the currents. These are all current profiles in a chip basically. And then from that, with the currents, you can tell whether there's an open, there's a short, and all of these stuff. You can figure it out. So I'll give you one interesting example here. This is a multi-chip module. This is a chip which has got like 4 layers which are separated by 40 microns. Okay, the current is coming from the bottommost layer. Okay, and it comes up, then comes to the topmost level which is closest to the detector, then goes back to the next level and then the lower level. So you can see there's a lot of information of depth here, right? What happens if you're far away from the detector, the information gets fuzzier and also it gets weaker, right? So actually we can use this to essentially measure Z. So we now have a major research program at National University of Singapore. They have the Center for Advanced Packaging. We're working with them to use AI/ML to essentially take a pattern like this and then try to fit the best current path that would essentially give you that magnetic field profile. So this is a very, very exciting problem that we are working on now. So so let me now, I will now come to the issue of memristors for neuromorphic circuits. And why is this important? Because today we all know about AI/ML. Everybody talks about AI/ML and so on. But the AI/ML, the rate at which AI/ML is growing is actually a bit slowed down because of the fact that it just costs too much energy, basically. To do the training of an AI/ML system requires training. That means it has to first learn, right? It's like us going to school first, right? So you have to put any AI/ML system, it's got to go to school first, and that costs a lot of energy, right? And this is where, and that partly because we are trying to use CMOS circuits, silicon circuits, and trying to adapt them for a job which they really weren't designed for. The CMOS circuits are damn good for what I would call digital logic, crunching numbers, that kind of stuff. But you ask them to do things like thinking kind of processes, it's very inefficient and it costs too much energy, right? So as a result of that, there's what we know right now is essentially, you can see according to this guy, essentially Jeffrey Hinton, he won the Nobel Prize, right? So this guy was the latest Nobel laureate, so raising the eyebrows of all physicists. But anyway, this guy basically said 80% of the world's data will be generated and processed outside the conventional centralized data centers or clouds. That means he's saying that all the AI process will have to be done what's called edge computing, basically. That means edge computing means you're not using the cloud. Okay, so we want to be doing all the AI ML processes within our cell phone without necessarily connecting to a cloud, basically. So that's really the constraint. Okay, so in order to do that your processes have to be incredibly efficient, right? Because we use a lot of we leverage the cloud when we do our computing for the AI/ML, but if you cannot use the cloud, that means your circuit has got to be incredibly efficient, right? And so the right kind of circuit is memristors. Memristors are circuits that enable you to keep the memory and the operation in the same place, right? So in the silicon technology, the problem is that it's called a von Neumann architecture, and there's what's called the von Neumann bottleneck, and that bottleneck arises because the memory is separate, the CPU is separate, right, and the data keeps shuttling back and forth between the memory and the CPU. So if you calculate the energy, it's not just the energy of the CPU, and it's shuttling the data back and forth between, that also costs a lot of energy, right? And for AI/ML operation, that part of the energy loss ends up dominating basically your total energy consumption. And that's why you want the memory and the CPU to be in the same spot. And in a memristor, it's like a transistor, but unlike a transistor, it actually has a memory exactly on top of itself. That's why it's called a memristor. Okay, so I would say this memristor takes the cake. This is essentially Sritosh Goswami, who was my graduate student at Singapore, and he developed this organic memristor system. And I mean, even till today, it amazes me that you can have an organic system that is so robust and can withstand so much harsh conditions and still survive and be so long lasting, which is very unusual. I think something to do with the bond structure of the ruthenium or whatever it is. I keep asking Sribrata Goswami, who developed these molecules, and still haven't gotten a full-fledged answer as to why these molecules are so stable, right? They're amazingly stable. I mean, you can heat them up in a vacuum to 500 degrees and bring them back and they still function. I mean, this is just too extraordinary. Anyhow, so these molecules show this. Here, for example, is the memristive state. This is not necessarily the ideal memristive operation, but it still shows its potential. And essentially, this could be one state, another state, right? But the thing about it is that this is what is so amazing about it. The endurance, you can go up to, you can switch them up and down multiple times, and it's like more than 10 to the 12 cycles, and it's still surviving. And here it's operating at like a, essentially higher temperature, about 80 degrees or so, and for 3 months without any change in the memory state. So this is pretty extraordinary, I would say. But what actually is even more remarkable is the field dependence. If you can enhance the electric field in these devices, then the switching voltages dramatically drop down from 4 volts down to sub 100 millivolts basically, and also their ability to carry larger current also increases dramatically. So these devices are effectively switching with ultra low energies. So I got one of my friends from Intel to give me the ITRF roadmap for memristors, and we collected all the different basically parameters that are required for a memristive device, and these are all the ITRS projections, and these devices literally beat every one of them, but not by a slight margin, but by a very large margin, almost all of them. So truly amazing device. And so recently there was another the ruthenium was substituted with iron, and this created totally new multiple memory states. So in a single transistor you have an on or off, but look at how many states that this device can have. So it's a phenomenal number of states, right? This gives you its potential, but that's not exactly the best way to utilize these memristors. So what Sritosh did is, this is the work done completely at Institute of Science, where he has essentially built the entire peripheral circuits, designed it all by himself, put the circuit there, and this is the entire, what I call India's first challenge to NVIDIA, basically. Okay, so anyway, so this circuit essentially was compared with other state-of-the-art circuit, showing that its performance is at least 4,000 times better than one of the state-of-the-art circuit, which is really remarkable in terms of its energy consumption and so on. Okay, but what was even more remarkable is the most recent work that Sritosh published in Nature, which is basically a device which produces 16,500 analog states. So basically 16,500 analog states, achieved by just by pulsing the circuit. You can attain different value settings of these things, and And so using this, he created a crossbar switch, and that crossbar memory was able to basically do a Fourier transform processing of a NASA data, and which is a frequency data, and convert that into an image. And this is the NASA computer built this image, and this is the image built by Sritosh's accelerator, and they're just about identical. The only difference is the energy consumed by this is 3 orders of magnitude lower than this computer, basically, state-of-the-art computer. To me, this really is an extraordinary accomplishment, and maybe, you know, this is something, this could be maybe India's major answer to the Silicon Valley here, basically, right? We could really introduce this as a, our first major product, okay? So anyhow, so I want to now go over to the last part of my talk, which is quantum, and what are we doing in quantum, okay? So in quantum, basically, what we're trying to do is developing essentially new qubits, quantum qubits. So right now, the conventional qubits people are using are, for example, superconducting qubits. Then you're using ion traps. Then you're also using atoms, single atoms, using the Rydberg states of atoms and things like that. So there's a whole bunch of things out there. I mean, nitrogen vacancy in diamond is another color center, which is also a very important qubit. But the problem with nitrogen vacancy in diamond is that the naturally occurring diamond has got a carbon isotope which has got some, about 1.03% of this carbon has got nuclear moment. Okay, but that is enough to really mess up your quantum state. Okay, so your quantum lifetimes become much shorter, 3 orders of magnitude shorter because of that. So the way around is to purify diamond, make diamond out of ultra pure carbon, which really drives up the price. Very expensive, right? So I started looking at the periodic table, saying, what else can we use? You know, it turns out that cerium and calcium are very interesting. These two elements have a lot of isotopes, but they all have 0 nuclear moment, you know, which is really interesting. So cerium oxide would be a fantastic nuclear host. Similarly, the calcium oxide would be a very good quantum host, basically. Problem was that the calcium oxide is, you know, very difficult to make actually. Cerium oxide, on the other hand, is easy to make. So we now have a big program for cerium oxide as a host for color centers, and we're doping cerium oxide with rare earth elements, and then we're trying to look for color centers by ion irradiation, creating vacancies in it. So that's a work that's ongoing right now. But I'll quickly show you some doping data. This is actually a what's called Rutherford backscattering and channeling data. And I'll only tell you what this data really represents. It shows that we have actually put thulium atoms in the place of cerium atom, and essentially we can do that to an accuracy of better than 95%, basically. 95% of the thulium atom goes sit in the cerium site, which is very beautiful, okay? And these are beautiful crystalline films we are able to make now, and so this is exciting. Same thing for terbium. We can do terbium atoms too. And these are the photons produced by thulium atoms. So these are basically thulium atom photoluminescence from the cerium oxide films which are doped with thulium. And now we're going to create some nitrogen oxygen vacancies in this and see if they form some kind of a color center with these states, right? So that's the next part of the study, right? So we are working on. Okay, the equivalent of the atom-based computer, quantum computer, is in an atom-based quantum computer. This is the idea originally proposed by Bill Phillips. Essentially, you take two sets of laser beam, parallel beams, and you interfere them. Then you'll create in space lots of maxima, minima, lots of minima. And when you put atoms in space, these atoms go sit in these minima, and you can create an atomic lattice completely by using the light beams. Okay, you can create the atom. The only disadvantage is that these atoms tend to hop out of these sites, you know, under slight perturbations, or you turn off the light, your atoms all go away, basically. So be really nice if I can make a solid state version of that, right? So in this atomic computer, how do you get entanglement? How do you make one atom talk to the other? You put them into the Rydberg state. In a Rydberg state, the radius of the Rydberg becomes very large in the Rydberg state. So that Rydberg state enables the atom to talk to each other and form quantum states, right? So what solid has that kind of a property? Do we have some solid which has got that kind of a thing? It turns out cuprous oxide is very interesting. Cuprous oxide is a material in which you have basically an exciton, and the exciton is very large binding energy of the exciton. It's almost like 100 milli electron volts from the bottom of this conduction band. Okay, so that gap is so much that we can look for Rydberg states in excitons. So people have now seen in single crystal cuprous oxide, it's a mineral found on Earth. Actually, you can get it out. And people have found in this Rydberg state up to 35. It's really remarkable. At 35, Rydberg state, the Rydberg radius is like several microns, and it's huge, right? So can we make films of this? So this material was discovered in 1953. People discovered it, but people are having a hard time making films of it, really difficult. So we started working on this material. So now we are now making these films, and this is the film made by Purdue, and you can see you can see how this looks like a rocky mess, basically, right? But each of this rock is like a single crystal. So you can see this Rydberg state. They can see this 1s exciton. This is a phonon assisted transition, and then you can see the first Rydberg state, 2, 3p, 4p. They can really see all this Rydberg state, right? Only problem is this is essentially a copper converted into copper oxide, cuprous oxide, and it's not a viable way. So now we're making PLD films of these. Ignore these particles. This we know how to get rid of. But now these are films, actually background films. When you go look at these now, these are PLD deposited films, and we can see the phonon assisted transition. We can see this very beautiful 1s exciton, and now you can see all the Rydberg excitons. Now you can see, you see 1, 2, 3, 4, 5, 6. So you can see them, right? And this is essentially done by photoluminescence. If we do resonant absorption measurement, we can probably see many more of these excitons in this material. So this work is really ongoing, and it's extremely exciting. All I want to say here, this is my team, the people that are working with me. This is Professor Horst Hahn. He came from Germany. He was the former director of the Karlsruhe Institute of Technology. He's an extremely highly decorated scientist. He's the fellow of the National Academy of Engineering. So he's kind of become big buddy with me. So we are working together very closely. And Honjong was someone we hired recently from Cornell, and he's an oxide growth person. Yasser is an AIML person. Vail is my project director for this Brathomics program. We have a small army of undergraduate students who I taught, who all volunteered to be in this program on Brathomics, and these are my postdocs and grad students. So I want to thank them for the work, and I want to thank you all for listening to my the cuprous oxide. So the first challenge for us is to learn to make it in a very uniform thin film. Okay. From the physics point of view, there are some really interesting questions. Okay, and that is, what does confinement do to an exciton? Right. In other words, for example, if I make the film different thicknesses, and every one of those Rydberg state has got a different radius, right? So what is going to happen to these Rydberg states in the that's the first question. Will they just undergo a frequency shift, or will they just not show up? What that's the first question. What does confinement do to them? Okay. Then the idea would be to essentially create. Remember the silicon pillars I showed? We will create a bunch of silicon pillars. The spacing, you can vary it. You can also vary the diameter, and then we deposit the cuprous oxide on top of it, right? And then what I'll do is I'll fill something like some kind of an optically opaque polymer, so that the material in the in-between layers won't show, right? And then we polish it back down, so only the excitons that are on top of the pillar, they will be exposed. Now I've got these various disks, right? Then I go to different Rydberg states, right? Then I can now induce entanglement between the exciton in one to the exciton in the other disk. What happens is there is a very interesting phenomenon by which within the Rydberg radius, if I excite one exciton, all the other excitons will become non-resonant, basically, by Stark effect, which is very beautiful because it automatically, you excite in a Rydberg radius only one exciton. So you get actually one qubit exciton here, another qubit. Now we can try to entangle them, right? This is a far superior system compared to the atomic system because I can vary the distances between these pillars as much as I want, and I can vary the diameter, etc. So there's a lot of flexibility here. And whereas in the optical ladders, your spacing is determined by lambda, right? So how do I get something very smaller? I discussed it with Bill Phillips. Bill Phillips, it's not a problem. You know, I'll come at an angle or something like that. I go talk to my other guys who actually do this trapping work. They all say, "Oh, it never works." You know, so what I'm saying is this is a much better, smarter way to build a quantum computer, right? Yeah. Using the state-of-the-art e-beam lithography, right, and reactive ion etching, we can make these pillars as small as 20 nanometers reproducibly, but there are some groups where they can do it even up to 10 nanometers. Right? Some really good groups can do it. Yes, I mean, if you can make something 10 nanometer, you can also make the spacing 10 nanometer. Yeah, you could do that. Same thing, yeah, of that order, right? So that's why it's important to know what does the confinement do to the exciton. Yeah, right. Does the surface tension effect become important?
Yes, because you're making small pillars.
Yeah. So you actually, your question is a very good question because if I showed all these patterns, right, these structures that grow on top of these pillars, they all tend to curve up like this. You notice that? They become like a earbud, basically, you know, look like a earbud. But the deposition is actually vertical, straight down. So why does it become like that, right? So it is surface tension, basically. The film on the surface as it grows wants to grow closer and closer and closer, and so it would have normally been the size of the diameter of the pillar. It starts that way, but then it starts becoming narrower and narrower, and it's sort of like a surface tension effect on the surface, basically, that pulls it in. Yeah, which is a very interesting point. Yeah. 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 Yeah, 10 points for a good question. But there's no bad questions, there are only bad answers. Okay, so any question is a good question.